Gosh, I guess. Hello. Hi. Hello. Great. Yeah. Let's just do this for half an hour. Sounds good. But yeah, hi. Thank you thank you for that. Hello. Before I start, my talk today is it's your callable or cool parts of Python's callable interface. And just before we dive into that, I'd like to say thank you to the organisers of this conference. The last time it went ahead was 2019. I was here, it was great, really kicked off for me a love of lots of things Python. And obviously since then we've had an enormous pandemic for the last 2 years. And then, just as we start planning it this year, we get things like rail strikes, and then I don't think anyone anticipated the sad death of the Queen last week as well. So despite all of those obstacles, thank you to the organisers for persevering this year so that we can all be here today. So, just before we, just before we kick off as well, I should probably explain who I am and why I'm here talking to you. So when I use this slide ordinarily to introduce myself around various different conferences in Europe, I normally have a picture here of maybe Big Ben or something embarrassing that's happened in UK politics in the last month or two to kind of introduce the UK and London. But obviously, you in this room will probably be familiar with all of that already, so I need to go a bit more local and try and just describe in an image central London, where I live, where I'm from. So the best I could settle with was this, unfortunately. But this is me. My name's Weldon, and I'm an independent contractor and a cloud software engineer based in central London. You can get a full flavour of some of the technologies that I use there. I'm a full stack person, but I do primarily use Python for most of my back-end work in software. I was working primarily for a long time for Decision Lab, and I'm still a principal advisor, associate, and just old hand there at the moment. But I currently work primarily for a City of London financial services organisation. I've decided not to name them here because I'm still relatively new, and also because I'm not in any kind of official capacity here. I'm just a guy that enjoys Python, talking here in sunny Cardiff on a Friday afternoon. The talk itself, like I say, it's your callable, bit of a rubbish pun, but just going through some of the cooler parts of the callable interface in Python. So why might you want to talk about this? Well, we know that functions in Python are first-class objects, and they're really kind of fundamental to how Python works. There are a lot of tools that you can use to inspect and introspect callables or functions at runtime. And they're really quite fundamental to a lot of the libraries that you probably use every day in Python, like PyTest, FastAPI, Pydantic, even things like Dask and various other libraries in the kind of data science world. We'll go through first off with a very quick tour of how callables work and some of the kind of quirkier features you might not be aware of. We'll look at how to inspect callables. We'll look at how to modify some of the data that's available on a particular callable or function. We'll review that and then have some caveats, and hopefully there should be time for some questions at the end as well. So, very quick tour of callables. First off, I should say, what do I mean by a callable? Well, quite simply, a callable is literally an object that we can call, or a function in most common parlance. We call a function with 0 or more positional and/or keyword arguments, and they return a value. So the most common ways you'll be familiar with creating functions in Python are these 3 ways. I think, someone correct me in the pub on this, but I think there are actually 7 different ways of creating a callable in Python, but the other 4 are just completely wacky. These are the 3 most common ones. You've got a def statement, an anonymous function, or like a lambda function, and you can just give a call method on an object like a class to turn it into a class that you can call like a function. So this talk today, I'm covering basically this particular line, or this part of the line of a Python function definition, so that def statement, where we look at the arguments and the signature and what it returns and so on. There is also this thing, a kind of cool part of Python called the Descriptor Pattern, which just you can see how, for example, the self argument ends up inside of a method. But I'm not covering that today. That's a kind of a topic for a separate talk. So this definition line is different from the other lines in a function because it's executed at import time. So when you import a module, your def statements run, but the code inside those def statements run, those def statements or that function code obviously doesn't run until you call it. So what happens when we run this particular def statement? If we use the dis module, or the dis package, sorry, to kind of look at what's happening under the hood, we see that we're creating two constants. One of them is a code block, and one of them is simply a name, f, and we're just assigning that code block to be accessible at that name, f. So if you inspect your function after you've written it as well, you can see that most functions in Python, certainly not all, will have this code dunder attribute on them. And that's a code block that, again, you can kind of look inside of and see there. You've also got this name attribute as well. So if you've got a variable that happens to be a function and you want to find out what the name of that function is, you can use this name method as well, which exists on lots of other objects and classes in Python as well. But callables can also be created inside of other languages. As you know, a classic one here is creating a function in Rust if you want to speed something up, or maybe C if you're feeling particularly brave, or Go or Java if you're feeling wacky. But yeah, I won't cover that in this talk either, but most of the metadata and the kind of introspection that exists on those functions, that exists on Python functions, you can do for functions in other languages as well, as long as you're kind of doing them properly. Some of you in the audience will probably also ask, hey, what about all this async stuff? Well, the short answer here is that I'm talking about callables. I'm not talking about awaitables. So your classic, if you're kind of familiar with the Python async world, you've got these asynchronous functions which generally return a feature or a coroutine. And we've got this function that you can use inside of the inspect package that will tell you if something's a coroutine function or not. A coroutine function is callable, but the coroutine that you get back isn't. Don't really need to worry about this. Basically, we're just covering everything that happens when you call a function, not when you await. So let's look at actually creating and using some of these callables here and the things that result from them, which are function signatures. Now, functions, as we think of them in Python classically, are actually two separate concepts inside of the documentation, inside of the language. One's an expression, and one is a statement. So if you think take the first example, which is the statement here. This is the function definition, and it's fully documented, obviously, in the Python documentation here in section 8, compound statements. And this statement doesn't return a value. All it's doing is it's creating this code block and slotting it into a particular name inside of your code. So we define the function here, and we say that a function has parameters. And I'll come to this in a second, but when you are defining a function, they're not arguments, they're parameters. Now, when we come to calling a function, that is actually an expression. Because it's executed, it takes a number of statements. In this case, it takes the function definition that we've written earlier, and it takes a number of arguments. And we pass these arguments to the function call. So function calls are actually documented in a separate part of the documentation in the primitives section, which is section 6.3. If you want some late night reading, if you suffer from particularly bad insomnia, say this. Now, the important thing here is that when we call a function, we actually pass arguments to a function's definition's parameters, and they're matched up. So we've got, on the one hand, a set of parameters that have been defined inside of your function definition, and on the other hand, we've got a set of arguments. And what Python tries to do is mash the arguments into the function parameters. Now that's important because Python has this cool feature where you can have variable numbers of arguments and keyword arguments, which I'm sure you've probably come across and used in the past here. So what happens is that in this instance, Python will say, oh, this function's been called with this particular combination of arguments. Can I make them logically slot into the parameters that has been designed for this function here? And I'm using this example function because you can also see that we've got a doc string here, which you're probably familiar with, and you can use to access documentation about your function as well. As of Python 3.8, 8, was it? Someone correct me if that's wrong. These new features came into the function definition as well, which you might not have seen yet, or might be using every day, who knows. But the asterisk at the top there specifies that everything to the right of that asterisk can only be defined as a keyword argument. And that slash that you see on the second function says that everything to the left of it can only be passed as a positional argument. And so if we try to pass those arguments incorrectly, like passing positional-only arguments as keyword arguments, we get a type error. And whenever that process of matching arguments to parameters fails is when we raise a type error in Python. Well, it's one of the instances when we raise a type error. You're probably also familiar with, since Python 3.6, you see these things, type annotations or type hints, and I love these. I think they're really, really valuable to the language, and they provide a ton of additional metadata that you can use inside of your code, and it just makes code far more readable as well, doesn't it? And so we've really got quite a lot of information about a function's definition when we write it, and I think of this as being like metadata about what a function actually does, and we can use it in our code. And that's basically how frameworks work. They use all of this metadata related to your callables that you've written, and use it to implement the features inside of that framework. So if you think when you use that, when you pass a route to FastAPI, where you're saying that this is like app.get, whatever. FastAPI is under the hood looking at all of that information that's been available on the function that you've passed as your route, and it does all of those under the hood. It uses all of that information to provide dependencies, specify route parameters, and all sorts of things. So this, knowing this kind of interface is really useful, because it allows us to build these frameworks and also to kind of hack into them if we want to get a feature in very quickly. We can also alter that metadata, which I'll show in a minute, which is an interesting example of something that can be quite useful. So just to recap some of the metadata that we've got available when we introspect a callable, what metadata do we have? So yeah, using this example function here that's got a nice positional-only argument, positional and keyword argument, and a keyword-only argument, plus some lovely type annotations. Let's look at the data that's available. We've got a name, obviously, got the doc string. You've also got the qualified name. So if your function exists in, say, some deeply nested package, you can find out what the fully qualified name of that function is. You've got the default values for positional arguments available at this defaults. You've got the keyword defaults available as another dunder property, sorry. And you've got the type annotations there that you can access. So if we look at that on the diagram, you can see that all of this information that you've provided when you're writing your function definition is actually available on your function to be used later if you're writing, say, a framework or you want to change something. In addition, we know that functions are first-class objects in Python, and I think it's important to ask what that actually sort of means, because we hear it said quite a lot. And so technically it means that a first-class object can be constructed at runtime, can be passed around as a parameter, returned from a function, or assigned into a variable. So what that means is that we can have functions, essentially code blocks or callables, flying all over the place inside of our Python code. And that's a good thing, it's a useful thing. But it does sometimes create a little bit of confusion, or can create some kind of messy examples here. So, for example, functions can be contained inside of another function. So here we've got this enclosed function, which is inside of that enclosing function. And it's dead simple, all it's doing is returning a value. Now, if we make that function a little bit more complicated and introduce a variable, you can see that here this function x is being defined in our parent scope. We are able to access the scope of our parent function inside of our enclosed function there. However, what about in this instance here? Do we think this code's going to work? Those who think it's going to work, put their hand up. Or those who think it isn't? Okay, does anyone know what's going to happen if I run that code? Well, we get this unbound local error. And what Python is saying here, essentially, is that we're on this particular line here, x equals x times 2, it's trying to find this value for x, and because we're already defining x inside of this child scope, Python isn't going to look in the parent scope to try and find it. So what we get here is simply an error. Python gets confused. It doesn't know where X is being defined. And so we can solve that using, because it's in the JavaScript, and we can solve that using this non-local keyword, which essentially will just tell Python that actually X is defined inside of that parent scope. Now, like everything with the function, that information is actually available to you at runtime as well about the scopes. So if we take this enclosed and enclosing example that we've got here, there's this dunder property called closure, which exists in Python, and you can look inside of that closure, because Python uses the term closure for this particular example here, and you get several different cells which exist as a tuple, and you can see what the values of the variables that are inside that particular code block are at any particular time, using the tools and the sort of code inspection tools that are available in the Python API. And if you've ever used a Python debugger, or things like PyTest as well, that kind of give you details about how your code's got run at runtime, they're basically using this as the starting point to make all of that work. This information all relates to a callable signature, which we can access using a special method that exists inside the inspect package, inspect.signature. And if we call inspect.signature, we get a special signature object, which is a class in Python that gives us really nice object-oriented details about a function signature inside of Python. And all of the individual parameters themselves are parameter objects, and we can access more properties of the parameter objects inside inside that particular signature as well. Now, just before we go on to how we might change some of that metadata, there's one important aspect of function calls in Python that I haven't covered so far. So if we look at that documentation of a function definition that I referred to earlier, you can see here, right at the very top, and just after the name of your function, is this decorator definition and syntax here. So you've probably used this before. We've covered a lot so far, but decorators are important parts of Python functions. They're essentially a function or a callable that returns another callable, and they wrap that particular function. And this decorator, like the def statement, is called at import time. So that's if you're using things like FastAPI or PyTest, where you use the decorator pattern to specify your routes for your web API or for your fixtures inside of a particular pattern. They're exploiting this decorator pattern, we call it. They also allow the function of the behavior of a function to be modified. Now, this is kind of the syntax that you'll use if you're calling a decorator when you're writing some code. But just before we kind of look at decorators perhaps in a little more detail, I thought I'd give a little side note. It's one of my favourite little fun Python facts lately. If we look at that definition again, this is the definition from Python 3.8. So this is slightly different from the one that I showed you before. But you see here we've got the decorators, and they refer to a dotted name. So in Python 3.8 beforehand, decorators had to have a name somewhere. That changed in Python 3.9 with PEP 6.4, and so you can now use Walrus operators or assignment expressions inside of your decorators, should you choose. So let's have a look at a nice, friendly Walrus operator. I should say, this isn't great Python code, so if you decide that you really, really dislike your colleagues, start writing some code like this. So this looks like a mess, and you can let you kind of maybe figure out what's going on here, but obviously that A is false, so we refer to the value on the right-hand side of the OR, and we just call it, we're defining a function, calling another function with some other stupid argument that returns another function, and it's valid Python, it will just return that one. As I say, only do this if you want to leave your job soon, or I don't know, maybe there's some ongoing feud in your office, but you really shouldn't be writing code like this. Still. So let's look at some of the function metadata and how that kind of pertains to decorators themselves. So I'm writing a decorator now. This is called announce call. And so all this is going to do is just before it runs my main function, or the function that it's decorating, is going to say, hey, I'm about to call whatever the name of that function is. We're using that dunder name there, and f strings as well. Beautiful part of the Python syntax. Anyone who's using the percent symbol stuff, just get on f strings. They're great. We've got this really simple decorator. All it's doing is announcing that we're about to call something. So we see how that works here. We're simple enough. So we've created our function with a new signature. Let's look at how this alters the metadata that we were talking about before, though. So we use this inspect.signature method, and oh dear, we've lost all of the metadata that we were talking about that's kind of useful and rich to use before. Now you might be aware of this, and I think all the Python tutorials you'll probably ever come across with decorators, they have a line in them that says that we have to use this functools.wraps, and never really expands on why. So you can see here this functools.wraps, it fixes the problem that I alluded to earlier, but how exactly does that work? And the short answer is, it works by adding this wrapped attribute to the function that it wraps. And all that wrapped attribute does is it points to the function which is being wrapped initially. Now that might not seem too revolutionary, but we can actually use this to great effect inside of other parts of our Python code. Now functions can be really deeply wrapped as well. So for example here we've got 4 different decorators all existing on the same function. But in this particular instance we can use methods like inspect.unwrap, and what that does is it follows all of these particular .wrapped attributes to be able to find that original function. So no matter how deeply nested your function is, so long as you implement this wrapped protocol, you'll always be able to find your original. Now, we've talked about reading that metadata, but what about if we wanted to change some of that metadata inside of a function signature? So it's a very quick challenge here. I'm going to create a decorator which adds a keyword-only argument to an existing function. So we're not changing our function as it exists at the moment, but we are adding a keyword argument to its signature. And we want to make that appear to any other tool that wants to instead ask, what's the signature of this function? Oh, it's got an extra keyword argument now. Now the example here is this isn't particularly useful code, but it's useful for demonstration purposes. I'm adding this shout option. So it's a decorator, and what it does is it adds a new keyword argument to the function definition here. It does some logic, so it asks, hey, does this function have a keyword argument called name? And if it does, it makes it uppercase like it's shouting. And then we're not going to pass that shout on because that shout argument on, because otherwise it would raise a type error. And we'll just use our decorator a bit like this, and hopefully in a minute or two's time we'll see that in action. I should say I am cheating here. I'm using keyword-only arguments just because it makes the demonstration simpler. You can do it with positional arguments as well, but it's a little bit more complicated. So how do we add that parameter to our to our code at runtime? Now, I've made that original function here a little bit smaller, so hopefully some people at the back can still see it, but it's the same code that was there in that decorator. Now, what we're doing here, though, is we're first off getting the original function's signature, and because we can use the object-oriented interface that I mentioned before with like parameters and signatures, we're creating a new parameter object here. There's 2 required arguments here, name and kind, and I think they called it kind because there are just too many instances of the word type meaning different things in Python. So the kind of argument here is a keyword-only argument. It's got a default value false, and the annotation is going to be a boolean. So now we're creating a list of the new parameters, so we're basically adding that parameter at the very end of all the other parameters. And we're creating a new signature using this replace method, so we now have a new signature object. Now, there's a caveat here as well, in that the signature object is a mapping proxy, whereas the argument that you pass to the parameters is a list, so you just have to convert them. It's an oddity, but c'est la vie. Now, just like that wrapped method that I mentioned before, though, Python also has this signature attribute. And if we, and the great thing about this inspect.signature method is that it will, like inspect.wrapped, it'll go through every single wrapped attribute to find the original function. But if any of those functions in the middle have a signature object, then it stops there and it says, oh, this is what the signature is to all of the higher up decorators. And so that's how you get this, this particular signature. So now we assign that signature attribute in our code, as you can see just down here. And now if we use inspect.signature on our original function, we can see it's got an extra argument in it, which in this case is shout. And we can say its default value is bool, and we get all of that metadata. Now you can see that, and we can also see that in the original function, though, if we unwrap that function to find the original definition or signature is unchanged. Now you can still use that function, create a greeting, just head up back in UK, and we can add that shout function and see that the logic is being executed, and that we are able to change the behaviour of that function or the arguments that are passed to it. As you've seen, you can alter a callable's apparent function signature using this the signature object and signature special attribute. You might ask why. There's a important point here. And so the classic examples are, for me, I kind of stumbled across this trying to write an integration between SQL Alchemy, Fast API and Pydantic before Sebastian Ramirez came along and scooped me with SQL model. But it's also very handy in lots of other situations, especially in AWS Lambda to remove a lot of boilerplate when you're writing or working with dependency injection frameworks. Final caveat, you might have heard of this thing called PEP563. Long story short, because I'm aware of the time, but basic answer is chill, don't worry about it. You can use type annotations in your code now at runtime, and it's cool. So, recap, Python callables, lots of rich metadata available on them. It's possible to modify this metadata at runtime. These are really, really important for developing frameworks, and despite some of the recent uncertainty with PEP563, type annotations at runtime is here to stay. So thank you very much. And I should say as well, I'll be around at the conference for the next few days, so feel free to turn up. Thank you.